Hello dear students, I am Dr. Sarika Kalra, Associate Professor in Electrical Engineering Department from Ajay Kumar Girl Engineering College, Ghaziabad. So, I am taking your subject Electrical Machine 1 and this is my 4th lecture. In the last lecture, I have discussed about the ideal transformer and how to draw the phasor diagram of ideal transformer. So, in ideal transformer, we have taken some assumptions. We haven't ignored the rotor resistance. Second, we have nullified the ignore the core loss, and third, we haven't considered the leakage reactance in the flux in the core, and last is we have considered the very small magnetizing current. But in practically, if you see the practice, but nothing is ideal in the there. I mean, so in practical, if you see the practicality of the transformer, you have to introduce all these things into the ideal transformer, so that you can imagine the how this practical transformer will behave. So, in the last lecture also these 4 which we have assumed in the ideal transformer, we just later in this lecture we introduce all these reality into the practical transformer. But before start with the practical transformer, I just briefed the idea of we have discussed in the last class, like in this case, in the last lecture we have discussed, like we have seen the ideal transformer and the voltage equation we get, and how the phasor diagram will draw at no load and at load in the case of load. So, whenever you apply the voltage V1 at a constant frequency 50 hertz, the transformer action takes place, and there is a EMF is induced in the primary coil. If there is a the load is not connected in this, the E2 will induce, and we have seen that E1 by E2 is equal to V1 by V2 is equal to N1 by N2. If the number of turns in the primary and secondary is N1 by N2. In this case, the E1 is equal to V1 in case of ideal, and the V2 is equal to V1 is equal to V2. And after that, when we switch on the close the switch, the Z2 will connect to the load side, and as the switch is closed, the I2 current will flow, and this I2 current will produce its own magnetic field, own magnetomotive force, which is N2 I2. So, when as the switch is closed, the primary will extract the I2 dash current, which is equal to the MMF produced by this I2 dash is equal to the MMF produced by this I2. So, this is the this I2 current will compensate by this I2 dash. So, N1 I2 dash is equal to N2 I2, that we have seen already. But in this case, the flux, the useful flux remains the constant, or the magnetizing flux remains the constant, either the switch is on or off. As the loading effect will takes place, the current as the secondary current will flow through the circuit, the same amount of current will draw from the primary side, so that it will compensate the effect of I2 N2, so that this core will maintain the constant flux, for constant magnetizing flux or the useful flux. Okay. So, the primary has at loaded condition, the primary has two current, that is I2 dash and IM, that is equal to I1. Okay. This we have already discussed in the last class. Okay. Today, these are the content of my lecture. Obviously, we are taking we are go through the module 1 single phase transformer. Now we consider the practical transformer. So after that we have seen that how the practical transformer is, I mean what are the practical transformer and how the phasor diagram will draw of the practical transformer. So like we assume in ideal transformer we assume that there is a no winding resistance, but in the practical transformer I mean you have like already know that there is nothing is ideal. So all this reality, I mean we inculcate to the practical transformer so that we can understand the how the transformer behave. So this first I have inculcated the core loss into the transformer. Second, we just now we consider the winding resistance of the primary or secondary of the winding of the transformer, and we inculcate the leakage flux into the ideal transformer, because we previously we assumed that all the flux which is produced by the primary, when we apply the voltage in the primary side, all the flux is confined within the core, but in reality it is not happen. There is a leakage flux which is which is the leakage flux, like if the primary side is there, so some leakage flux in the primary is present, and some leakage flux which is connected to the secondary winding which is present. Third, like last we have seen that there is a finite current, I mean there is a in the last ideal transformer we have seen that the magnetizing current is very small and we can assume that it is vanishingly 0, but in practical transformer we have to assume that it has some finite value. Okay. So first case I have considered like effect of core loss or introduce of core loss in a ideal transformer, so that we can familiar about the practical transformer. Okay. So as you know, the core loss is equal to the hysteresis loss plus the eddy current loss. Obviously you know that these are the losses, or these do the introduce the power loss in the transformer. So the core loss is the sum of hysteresis loss plus eddy current loss. So if we see the eddy current loss, and these losses we will discuss in detail later, but I just see the brief idea so that we can inculcate this losses into the ideal transformer. So eddy current losses, because there is a changing flux in the core. So due to this changing flux in the core, like suppose this is a cross section area of the core, this is flux, suppose I have taken this kind of, the one limb of core, limb of transformer. So this is flux and this is changing flux. So it experience a close path near to the flux. So these are the eddy currents which is flowing in the core material of the core. So obviously if there is a ferromagnetic material, there must be a eddy current losses. So to nullify this or to minimize this losses, we use the laminated core. Okay. And the formula of the eddy current loss and the formula of eddy hysteresis loss we will take in the next coming classes, but right now I am just give you the brief idea how this core loss will affect the working of the transformer. Okay. So hysteresis loss, now this is the loss, this is the circulating current which is produced in the material of the core and it is closed path core. So, these are the eddy currents. So, if you take the lamination of this core, you can minimize the eddy current losses. Okay. So, now see the hysteresis loss. Okay. So, if you draw the no load power factor of two winding transformer of ideal transformer, as you remember, there is a flux, the reference flux, and there is a voltage E1 and E2, okay, and there is a very small magnetizing current, but in case of this practical transformer you have take the some large magnetizing current, because the core material is not the it's highly permeable, that is fine, but it is not up to the the permeability is not a infinite. Okay. So, this is the phasor diagram of ideal transformer. Now, how this hysteresis loss will inculcate into the ideal transformer? Like if you see the this BH curve, H or I, this is B or flux. Okay. So, this is BH curve, and according to that you can draw the suppose this point is A, okay, and this is suppose O, this is B, and this you have to draw with respect to time. Okay. Now, at this point OA, or you can say this is maximum minus H and this is sorry okay. So, at this point A point, you just see that at this point H or the magnetizing current is 0, but there is a flux which is the negative value. Suppose corresponding to this so corresponding to this A point, this A in at A point you see that the H is negative sorry 0, or the current is 0, but the flux is a negative value. So, at this point suppose at this point the current is 0 and suppose it is a somewhere here the negative value, and this is 0. Okay. Now at this particular point B, this is a point corresponding, at B you just see that there is some current, but the flux value is 0. So there is some current, but the flux value is 0. After that you just see at this point it is a maximum, but both have some finite value. So you can draw, I mean you have an idea about, like, this is suppose the current and this is the flux. So due to this hysteresis loop, this is called the hysteresis loop of the material. So due to this hysteresis loop, you have seen that this A point is, the flux is, in this case the flux is negative, at that same point the current is 0 value. As it will reaches to the 0 value, the current has some finite value, and this you can conclude from this things that the current is, that is magnetizing current, or you can say IE, the exciting current is, the name term comes here, the exciting current, or you can say, so exciting current is leading with the flux phi. Okay. And why this IE is leading? Because of this presence of the hysteresis loop. Okay. So in this phasor diagram, you can draw, now the current will become like this. In the case of ideal, only the magnetizing current is there and it is in same phase with the flux, but due to the presence of the hysteresis loss, there is the BH curve is not a linear, it has this kind of loop. So due to this loop, you will see that the current is lagging with the flux. If the current is lagging with the full flux, so you can draw in phasor diagram, this core loss is inculcate in the phasor diagram. So the IE is lagging with the flux, suppose this angle is alpha, and this is called the hysteresis angle. So the angle, suppose this is instant WT1 and this is instant WT2. So the angle between the current and voltage is suppose alpha, and this is due to the hysteresis loop. And this is called, alpha is called the hysteresis angle. Okay. So the presence of this hysteresis loop, the current is leading with the flux phi. Now the phasor is like this, so you can distribute this phasor into a two phasor. So one is the magnetizing current, which is same phase with the flux, that is only responsible to produce this constant flux. Okay. And one component, this is the IC, that is called the core loss component, and this is present due to this hysteresis loop. Okay. So how this core losses inculcate into the in the ideal transformer, this is how you can see. The I is due to this hysteresis loop, I is leading with the flux, so it can be divided into a two component, but the IM is the useful magnetizing current, which is responsible to produce the useful magnetizing flux, constant flux, and this IC is the core loss component. Okay. So this is the core loss component, and if you reduce the width of this the hysteresis loop, you can reduce the value of IC, okay, and reduce the hysteresis losses. Okay. So, if you see that, like if you compare the two hysteresis loop, and suppose the another hysteresis loop is so this gives you the less core loss in comparison to the this hysteresis loop. So, this is suppose one hysteresis loop 1 and this hysteresis loop 2. So, the hysteresis loop 2 will give you the less core loss. Okay. Why so? When it is less, then I towards, if the loop is less, the width of the loop is less, so the hysteresis angle become low. So, if the alpha is the hysteresis angle. Hysteresis angle. So, alpha I tends to towards to more this I. So, if it is I towards to more like this, so the IC become less. So, the IC become like this only. In this case, the IC become length of the IC become like this, and if the angle of alpha will reduce, the I more towards the tends to the flux. So, the IM is larger and the IC become less. So, the core loss become reduces. Okay. Now, so this is how this the hysteresis loss or the core loss will inculcate into the ideal transformer. Now, second thing, how to I mean in ideal transformer we assume that there is a no winding resistance. So, how to inculcate the winding resistance, because the no winding has I mean it is ideal, there is a some resistance. So, agar resistance hai, if there is any resistance, so there is a voltage drop. Okay. So, suppose this is an ideal transformer. Now, how this ideal transformer become a practical when we inculcate all this parameter in the ideal transformer. Okay. So, resistance, obviously this, if the supply voltage is suppose V1 and here the E1 is induced, here the E2 is induced, suppose there is a switch and there is a load in this. Now, if you consider the winding resistance, that means in case of ideal, the V1 is equal to E1. So, all the flux which is produced by the V1 will confine within the core, and this E1 is equal to the V1. But in case of practical transformer, if you consider the winding resistance, we have obviously this winding resistance should be in series, and it is we consider as a small. So, this resistance suppose we have considered. So, due to this resistance V1 is not equal to now E1. This resistance will create a, suppose this is R1, this resistance will create a, and here suppose this is no load. So, the I will flow, will create a voltage drop across this I1. So, this will create a so, now your V1 become equal to IE R1 plus E1, the phasor sum. Okay. And how this will inculcate into the phasor diagram, we will see. Okay. So, now if you consider the effect of leakage flux, how this leakage flux comes into the picture? Now, suppose this is V1, this is switch, or you can draw the like okay. Now, you eliminate this, just a second, you eliminate this core, I just draw the equivalent circuit. So, as we apply this V1, the flux will produce, and this flux is the magnetizing flux which is confined within the core only. Okay. Now, but due to the presence of leakage flux, some flux is connected through the primary winding only, and some flux which is connected through the secondary winding only, and this magnetizing current is confined within the core, but this leakage flux is confined within the air only. Okay. So, suppose the leakage flux in primary winding is equal to phi L1, and simultaneously in secondary winding that is phi L2. So, this is phi L1 and this is phi L2. Okay. So, these leakage flux is due to, I mean, it is confined in the air gap, in the air, not a gap, and this phi L1 also the phi L2. So, second, phi L1 is linked only with the primary winding. And third, phi L2, similarly phi L2 is linked with only secondary winding. Okay. So, that means this flux is not useful flux, only the phi m, the magnetizing flux is the useful flux that will create the, I mean, takes place in the transformer action. But these fluxes are, which is linked only the primary winding or the secondary winding, is not a useful flow, that will create a voltage drop, because it is a kind of changing flux, So, phi L1 and phi L2 also are changing flux. So, that will create a EMF induced. So, d phi L by dt will create a small EMF induced in the primary side, and this EL2 will also create a small voltage drop across the secondary winding. So, due to this voltage drop, we inculcate a reactance value in series with the source, reactance value in series. So, we inculcate the reactance value in series with the ideal transformer. And that will create a voltage drop across the, that will create a voltage drop. Okay. So, due to the resistance also the voltage drop takes place, and due to this leakage flux the voltage drop takes place in the primary as well as the secondary winding. If the secondary winding is loaded, then there is a voltage drop across the resistance and the reactance, and if it is no loaded, it is present in the primary side. So, if in the previous slide if you see, like in this, we introduce this winding resistance. Okay. Now, in this case, now we introduce the, if you draw another equivalent circuit. So, in this case we introduce the leakage reactance in both the side. So, it is X1 and suppose it is XL2 and XL1. Okay. So, if you draw that another circuit in which this is the resistance and leakage reactance, and this is also the resistance and leakage reactance. Suppose this is ideal transformer, this is R1, this is XL1, this is R2 and this is XL2. This is present due to the winding resistance, and this will present due to leakage flux. Okay. So, that is why this E1 is not equal to the V1 and this E2 is not equal to V2, because it has some drop between the E2 and V2. Okay. Now, and this magnetizing current is a finite value and it is not 0 at in case of ideal transformer, that we have already discussed, because the magnetizing current is that in ideal transformer we have already considered, but in this case there is a much larger length in the case of practical transformer. Okay. So, I just use this page. So, if you see the previous slides, how this you introduce, first is the core loss you introduce. Okay. Second thing, you introduce the winding resistance. Third thing, you introduce the leakage reaction. So, the combined circuit will become R1, X1, R2, X2. Okay. So, you just see in the previous slide, like now you introduce the resistance, the leakage reactance, and the, due to this hysteresis loop, you introduce the IC current. Okay. That is core loss component. So, finally, we achieve that. Suppose again we draw the diagram, so that you have understand finally how you will get, how this all three we inculcate in the circuit. So, this is the ideal transformer. Now, we introduce the resistance, the leakage reactance. In the other side, you just insert the resistance and the leakage reactance, and this is load. So, this is R1 XL1, this is R2 XL2, and what about this? Suppose this is the V1 supply voltage. This is the ideal transformer. So, how this you inculcate the, we will see the equivalent circuit later, but now we just, I am just introducing the resistance and the leakage reactance. Okay. This is S and Z2. So, in this case, the V1 must be equal to, suppose at no load, I is there. I, why this I? I is the phasor sum of, so this R1 plus XL1 IE plus E1. because it should follow the KVL. So, V1 must be equal to I R1, it is Jx1 and plus I, these are all the phases. In this side, suppose this S is closed, so the I2 current will flow here. So, this will satisfy the KVL also. So, this V2 is not equal to E2. Okay. But in case of ideal transformer, V2 has to be equal to E2 and V1 is equal to E2. But in case of this, there is a drop between the R2 and the leakage due to this leakage reactance. So, the V2 is equal to E2 minus I2 R2 plus JXL2. This equation come into the picture when the transformer is loaded. And this is when the transformer at no load. So, this you have seen that how this all three reality is introduced in the practical transformer. Now, we combine all these things and draw the phasor diagram at no load. Okay. So, you just see that take the flux as a reference voltage. Due to this flux, E1 and E2 will induced, and the length of the E1 and E2 depend upon the number of turns which is present in the primary and the secondary. Suppose the N2 is less than E1, sorry N2 is less than N1, so the E2 will be less than E1. Okay. Now, due to the this flux, you have already seen due to the presence of hysteresis loop, the current is leading with the phi, and this angle is the hysteresis angle between the flux and the current, and this current is called the exciting current. So, we if the phasor is like that with the reference to this phasor, so you can divide into a two part. Suppose this is Im and this is Ic. That means I is phasor sum of Ic plus Im, where I is called the exciting current, Ic is the core loss component, and Im is the magnetizing current. Okay. Now, the transformer is at no load, that means I2 is 0. So, in the primary side only this exciting current will flow to compensate this magnetizing current and the core loss component. So, the supply draw the exciting current. Okay. Now, and this IC can be reduced with using the material which has the lower width of this material. If this is if the BH curve is like this, less than this BH curve comparatively, so this material has the lower core hysteresis loss or the core loss, you can say. Now, in the primary side, if you see the previous diagram, suppose this E1, you just take the one term V1 dash. Okay. So, I just take the V1 dash phasor which is equal to the minus E1 to draw the phasor diagram of the primary side. So, I just taken E1 is equal to minus V1 dash for this to explain this thing. To take the phasor opposite to E1, suppose one phasor is V1 dash and it is equal to minus E1, because you have to draw the phasor diagram now in the primary side. So, I just taken V1 dash phasor. Now, if you see this diagram, the equation satisfy this, because V1 is only the source. By using this V1, the transformation action takes place, the E1 is generated, but there is some drop in the resistance and the leakage reactance. See? And in the resistance there are drop is IR1. So, IR1 is the drop in the resistance. So, the resistance, so the drop is the voltage. So, the angle between the current and the voltage drop across the resistance is 0, because it is a resistive. So, if you draw this equation in this phasor diagram, E1 you have taken like this this V1 dash, and now add this IR1. So, if you add E1 plus IR1, this voltage must be same phase with the current, and the current is I. So, this voltage is same phase with the current. I just take small. So, this IR you can draw like this is IER1, because this voltage drop is the R1, R the resistance is there. So, the voltage is same phase with the current. So, IR is same phase with the current. So, I just draw the voltage is same phase with the parallel to this I. Now, you have to inculcate this leakage reactance. So, the voltage drop across reactance is IX1 and it is a inductor. So, the voltage is always leading with the current. So, this IXL1 voltage drop is leading with this I current. So, now if you want to inculcate this IXL1, the voltage should be lagging with this current with the 90 degree. So, you have to draw the phasor in 90 degree with the I. So, this is like this. So, this is IEXL1. Now, this total voltage will give you the this is V1. Okay. So, one equation is this and other is V1 E1 plus I R1 plus JXL. And secondary side is there is no current, because I am drawing the phasor diagram at no load. So, this is the phasor diagram at no load. Okay. So, in this E1 and E2 is there, the I is the sum of the phasor sum of IC plus IM, where IC is the exciting current, I is the exciting current, IC is the core loss component and IM is the magnetizing current. So, if you draw this V1 dash, this E1 plus IR1 plus XJL1. So, IR1 voltage is same phase with the current and this is the reactance element. So, always voltage is leading with the current with the 90 degree, that is why it is a 90 degree. So, the sum of this E1 IR1 IXL1 is give you the V1. So, this is the phasor diagram of practical transformer at no load. Now, we see the how this phasor diagram draw at a lagging power factor. If the load is a kind of inductive kind of nature, so you have to draw now. So, if we consider this circuit, now this switch become closed, I2 start will flow, the current I2 will flow. Okay. Now, if the I2 as switch S is closed, I2 will start flowing. And it produces its same I2 into magnetomotive force. So, similarly in like previous in ideal transformer, we have seen that the due to this I2 current, a compensating current will flow in the primary. As the transformer is get loaded, the same amount of current which is equal to the secondary current will flow in the primary side of the transformer. So, that in primary side of transformer, suppose the current is I2 dash. So, the MMF produced by the the primary side is N1 I2 dash, and this must be, so this current I2 dash must be nullify the effect of this MMF of the loading effect. Okay. So, in primary side, when the transformer get loaded, the current will be magnetizing current plus the loading component. Okay. Now, if you draw the phasor diagram at load, lagging load, suppose the flux is there, this is E1 and E2, and suppose the power factor angle is theta. When the load is connected like this, the power factor angle is suppose theta 2. So, angle between the V2 and I2 is, suppose the angle between the V2 and I2 is theta. Now, suppose your V2 is this is V2 and this is I2 and this is theta. In case of ideal transformer, V2 must be equal to E2, but in case of this practical transformer, V2 is not equal to E2. There is some drop between the V2 and E2. Okay. So, this I2 is suppose flowing in the secondary side. Now, here is IM, this is IE, suppose no load current, which has two component IC and IM. Okay. To compensate this current, in primary side there is current which is flowing in the primary side. So, that must be equal to I2 dash. Okay. Now, the phasor sum of I2 dash and Im gives you the primary current. So, if it is IE, this parallel to IE, so this give you the I1. This is the primary current. Okay, because at loaded condition both the current is flowing, that is IE and I2 dash. So, IE in the ideal transformer only Im is there, but in case of practical transformer IC comes into the picture. So, the IE is leading with the flux, and another current when the flux is the transformer is loaded, the same current will flow into the primary side also, that is I2 dash. So, the phasor sum of I2 dash and the IE will give you the primary current I1 when the practical transformer get loaded at a lagging power factor. Okay. Now, how you draw this V1? Same as in case of the no load. Now, take the V1 dash. Suppose this is V1 dash which is equal to minus E1. Okay. That must satisfy like V1 is equal to V1 dash, or you can say E1 plus I1 R1 plus J XL1. In case of no load only this I current is there, but in case of this lagging power factor now this I1 is there, because it is a phasor sum of I2 dash and Im. Okay. So, this how you can draw this. So, the voltage drop I1 R1 is same phase with the I1, this is I1. So, if you add this voltage I1 R1 into the V1 dash, you just parallel to this I1, because both are in the resistive circuit is there, and so the I1 R1 are in same phase with the current. Now, due to this inductance, it must be the voltage must be leading with the current. So, the I1 is current, the voltage drop is leading with this I1 current by 90 degree. So, this is I1 x L1. So, this becomes V1. So, V1 is equal to V1 dash I1 R1 and I1 XL1. Now, on this side you just see that this V2 is not equal to E2. There is some drop due to this I2 current and due to the presence of resistance and leakage reactance. So, when the I2 current will flow, there is a drop in the resistance I2 R2 and drop is the leakage reactance is I2 XL2. Okay. So, this will you can write this E2 is equal to V2 plus I2 R2 plus JXL2. Now, you add in V2, this give you the E2. So, in V2 you add just I2 R2 and this is V2, this is I2 R2, and this is I2 XL2. So, this voltage is 90 degree with this current. So, you can rub this. Now, this has become E2. Okay. So, this is E1, this is E2. So, this is the phasor diagram of the practical transformer at a lagging power factor. Okay. Now, we see similarly we can draw the phasor diagram of practical transformer at a leading power factor. That means, if the load is capacitive kind of nature, that means if the current is the I2, the load current is leading with the voltage. So, how you draw this lagging power factor? This also you can try in at your for practice. Also I can draw this is suppose phi, this is suppose E2 E1, and suppose this V2 is here and I2 is here. Because it is capacitive, so the angle between the V2 and I2 is the voltage is, the current is leading with the voltage theta 2. So, the power factor is theta 2. So, in this case the current is leading with the voltage, that means it is the capacitive kind of nature. Okay. Now, same, the no load current is, suppose exciting current is I, it has two component IM and IC, and if the I2 is there, the compensating current will flow in the primary side, that is equal to to nullify the load effect, equal to the I2, that is I2 dash. So, phasor sum of this I2 dash and IE will give you the I1. Okay. And suppose this is your V1 dash, where V1 is equal to V1 dash plus I1 R1 plus I1 J XL1, and I is equal to IM plus IC. So, add this I1 R1 I1 J XL1 into the V1. So, this is I1. So, this is I1 parallel, I1 R1 is parallel to this I1, and I1 XL1 is 90 degree with the I1. So, this give you the V1. Okay. this is your I1 R1 and this is your I1 XL1. Now similarly in this case E2 is equal to E2 is equal to V2 plus I2 R2 plus I2 J XL2. So similarly you can draw here V2. In V2 you can draw parallel to this, the I2 R2 is parallel to this current. So parallel to this current and it is 90 degree with the this. So this is your I2 R2 and this is your I2 XL2. So this you can so your E2 become, this is suppose E1 and this will become E2. It is phasor sum of V2 plus I2 R2. I2 R2 is the voltage drop across the resistance, so that the voltage will be same phase with the current I2. So it is same phase with the current parallel to this I2. And what about this I2 XL2? XL2 is the element, the inductive element. So this drop will, this voltage will leading with the current. So it is parallel leading with this current by a 90 degree. So you can draw like this, okay, and this will become your E2. So this is how you can see that how to draw the phasor diagram when the some practicality added in the ideal transformer or some reality add to the practical transformer, how this practical transformer behave and how to draw this phasor diagram at a no load, and we also see the how this phasor diagram drawn at leading power factor and the lagging power factor. Thank you all, and in the next lecture we will see the equivalent circuit of the practical transformer. Okay, and if you have any query, you can contact me on my email ID, that is Kalra Sarika @Ajay Kumar Garg Engineering College, or you can write like @akgec.ac.in. Thank you.